Hello and welcome to the flipped instructional session for Physical Science Semester A. Today we're talking about 1.03 Science and Engineering. So be sure you're taking notes during the recording. I'm going to give you keywords and concepts that are important for you to write down. And be sure you title your note page with the lesson number and title. So as we get started today, we're talking about science and engineering. All right, and as we get in, we're talking about bungee jumping. Must be an exhilarating, and what could go wrong? Actually, a lot. So after you watch a few people go, you might decide it's a safe enough thing to try. But what would you want to know if you were the person to try it? So check out this video and think about it. All right, so as you're watching this person dangling in the air, things that you might be thinking about. One, the strength of the bungee cord. Is it strong enough to hold the jumper? Is it too springy? Will the jumper get pulled up too fast and get hurt by the sudden change in direction? Or is it not springy enough and the jumper would hit the ground before getting pulled back? And those are just a few things. So before jumping, you want to collect a lot of data to verify that you would be safe. All right, so our lesson goal today is to define universal law and be able to give an example of that. All right, so as we jump into explore, let's talk about understanding phenomena. Scientists build knowledge to understand phenomena. So as scientists, our goal will be to understand physics so that we can explain and predict phenomena. A phenomenon can be something as simple as this. Objects fall to the ground when dropped. Pretty easy, right? So scientists like Galileo observed this phenomenon and wondered why they fall and what else is true about falling objects. Galileo asked questions like this: do all objects fall at the same rate? So now we bring in engineers, and we're trying to understand how they think and what they do. So engineers use science to design solutions to problems. As engineers, we'll use our knowledge of phenomena to design or evaluate solutions related to the phenomena. So Orville and Wilbur Wright understood physics, but they didn't study it to broaden our understanding of the natural world like Einstein. The Wright brothers applied their understanding to build and fly the first airplane. They were engineers and they used physics to design a solution based on physics principles. Physics involves both science and engineering. So a glider is similar to a plane, but it has no engine. A plane tows the glider into the air, releases it, and then slowly glides to the ground. So pan and zoom around the glider image. Think about how science and engineering are used in design so the glider responds to force and motion. So we can kind of look all around to see what's happening here. You can see this glider in the air, the direction that he's going. Okay, so we have a good idea of what's going on here. So scientists, they develop a knowledge base that allows us to understand the forces that act on an object as it moves through the air. So first you learn about the science of these forces so that we're able to design something. So an engineer would take that scientific knowledge and use it to solve a problem. And then society, that's scientists and engineers, contribute to society, but they do it in different and complementary ways. So scientists work to understand physics. So as scientists, we want to know what kinds of forces are at work on a structure and what happens when the forces are not balanced. A scientist is concerned with making sense of the way gravity and friction work, how the strength of the materials work together, and how those materials behave over time and under different conditions. For example, a scientist is researching building materials. He is studying how the steel behaves when it is compressed and pulled. He will record his findings and share them with others who may contribute to the body of knowledge with their own observations and experiments. So here's some important things that you're going to want to write down. Scientists use hypotheses, laws, and theories to describe the universe. So a hypothesis is an educated guess, a testable guess, that predicts how variables are related in an experiment or a model system. And it's often expressed as an if-then statement. So remember this, and this is an important thing to write down. Remember, you can always pause the recording to get those definitions. But an if-then statement says, if I do this, and you give your set of testing guidelines, then I should see this. So that's an if-then statement. You're telling me what you're doing with what set of experiment guidelines, and then what you think is going to happen based on that. So a theory is an explanation about the natural world that has been repeatedly confirmed through observation and experiment and accepted by the scientific community. So you can see that it is different than a hypothesis. A theory is something that's been tested over and over and over, and we're pretty much accepting that as fact. And a law, that's a description of the relationships between observable phenomena. So in physical science, you'll hear all kinds of laws. Laws of gravity, law of conservation of mass, law of conservation of energy. So a law, it explains how the relationships work. So theories and laws work together to explain and describe the behavior of physical systems and the universe as a whole. So people have misconceptions about ideas, theories, laws, and hypotheses. Let's clear them up. A scientific theory isn't the same thing as the common theory that you hear people talk about in everyday language. When people say, hey, I've got a theory about that, they usually mean they've got an idea that attempts to explain something. So many people think hypotheses become theories and that theories becomes laws, and that's not true. Collectively, hypotheses can help form scientific theories, but they don't become theories on their own. And theories don't become laws because theories and laws are different things. Laws are statements that describe phenomena, and theories help explain phenomena. So make sure you have that written down. You understand the difference in a theory and a law. And then, for example, we have laws of gravity that describe the way gravity works. We have a theory of gravity that tries to explain how gravity works. And the law and theory need to work together, but a theory doesn't become a law. Scientific laws are universal, and this is an important concept. You'll see this again on quiz and test questions. A universal law is a principle that is in effect everywhere at all times. So that's the definition you need to get down. And an example of a universal law is the law of gravity. So you could write down that example as well. And what that law says is any two masses have a force of attraction between them. Physical scientists think that this law applies to any two masses in the universe. So think about it, gravity is universal as well. So in your study of physical science, you will encounter many universal laws. Examples of universal laws include the laws of conservation of energy, the law of conservation of momentum, and Newton's laws of motion, which you will learn about in future lessons. Engineers use physics to solve problems through design. Engineers are interested in using science to solve problems by designing solutions. Mechanical, structural, civil, and electrical engineers are all examples of engineers who are interested in using physics to solve problems. Packaging engineers consider which materials should be used to protect fragile items. A person can certainly be both a scientist and an engineer, but the disciplines of science and engineering have different goals. The goal of science is to broaden our knowledge base. So that may be something you want to write down. The goal of engineering is to design a solution to a problem. That would be a good thing to write down as well. Sometimes that problem may be very practical, like designing a bridge to get across a river. In other cases, the problem may really be an opportunity to design something that inspires people. In this course, we'll continue to make sense of the world through physics. We'll focus on studying forces and motion, and then we'll apply what we know to create or evaluate design solutions. Science, engineering, and technology are interdependent. So as scientists work to better understand the universe, engineers apply new scientific discoveries to create new technology. New technology better helps scientists understand the universe, and the cycle continues. So we're looking here, the scientist is using a scanning electron microscope to look at the surface of new material. Science, engineering, and technology influence society. So sometimes the technology developed is used directly by people in society. Mobile phones are one example of technology that has a large influence on society. Consider some of the technology that you use every day and how your life would be different without it. All right, so this is a simulation that uses blocks and springs to model jumpers attached to bungees. So think back, we started talking about bungee jumping at the beginning of the lesson. Each jumper has the same mass, but the springs are different. So evaluate the design of each bungee by dropping the jumpers from different heights. Jumpers want a long drop, but they don't want to hit the bottom. The jumpers are suspended from above foam blocks. Evaluate each bungee by lifting and dropping the jumper. Find safe drop points that let the jumper touch the foam pit just a bit without hitting the ground below. All right, so if we replay, you can kind of watch A first and see what happens. Okay, so if I play it again, A hits the ground pretty hard. So it is not passing the, touching the foam pit just a bit without hitting the ground. It is actually hitting it pretty hard. So now watch B. B seems to hit it with the same intensity, right? They seem to both, A and B, be equal there. Okay, and now let's watch C. C has a lot of spring, and it doesn't look like it hits the foam pit at all. So let's see, what are the two design criteria that we need to consider here? The two things is that they want a long drop. So C didn't really give as long of a drop, and that the jumpers cannot hit the bottom. So A and B both hit the bottom. So what is the best drop height for the bungee A? You can measure from the bottom of the orange bungee. So it does let us play with that a little bit and do some different things. So if we pull it, now we took it off. We don't want to do that. Reconnect. Let me see if it'll reset it. It should let me. There's the reset. It's not resetting it. Okay, so let's try our drop for B. I'll try it at 80 and see what happens. Okay, it's hitting the ground too hard there. So now let's try it at 70. That seemed about right. And then let's try this last one. We can see that this one looks like it's a little more tightly coiled. So we don't want to probably start it, we'll see, at 80 what happens. It doesn't go very far. Uh-oh, I just connected that one too. Let's see if it'll let me hook it back. There we go. So this one could hook back too. Kind of tricky to grab it. I won't connect back. All right, so for this one, we could try dropping 90. Gives us a pretty long stretch, but you can see the different scenarios that can happen. So what's the best drop height for bungee A? So there we saw close to, but not over 50. So this range here would keep it from hitting the ground. And then the best drop height for B would be 55. So it could go a little higher, but it doesn't touch the ground, so 55. So not really a great drop height. And then what about for C? The best drop height for C is 70, which is as high as you can go. So right about here. So which bungee and drop height best meets the design criteria? So the best bungee at the height of close to 55 is, so it's B. And so we can see that it meets both of those. All right, so we have finished talking about 1.03. Make sure you have your notes together on that, and you'll be able to move on to the next lesson. And in doing that, just look for the flip follow-up that you may see. And if you have questions, please let me know.